All right, so welcome back for part two of section, what is it, 7.3, 7.3, that's it. We're still working with probability. We're still looking at experiments and finding the probability of doing some event. For this example, we're going to take a look at a deck of cards. For the homework, for the class, for the exam, this is going to be our deck of cards. Our deck of cards contains 52 cards, so it is a standard playing card deck. There are 52 of them. There are 4 suits. The suits are the hearts, the clubs, the diamonds, or the spades. You notice that there are 2 red suits, and there are 2 black suits. There are 13 cards per suit. Whoa, I don't want that one. There are 13 cards per suit. Right? Face cards are jacks, queens, and kings because those cards actually have faces on them. You'll notice that aces are not face cards. There are no faces on aces. Okay? You might live in a world where you think an ace is a face card. That's not true for this, and it's not my rule. It's the rule of the book, the homework. When it asks questions about face cards, it's talking about jacks and queens and kings. Okay? All right, so here we go. Our experiment is a card is drawn from a well-shuffled deck. So our sample space then is going to be all 52 cards. You notice I'm using words for this rather than using roster method because I'm not listing them all out, but it's these cards right here. It's all 52 of them. That's our sample space. What is the probability that we will pick a 9? So my event, and I'm just going to call it E for lack of a better thing to call it, is going to be the ways that I can pick a 9. Well, there are 4 ways I can pick a 9. I could get the 9 of hearts. I could get the 9 of clubs. Let's see if I can draw a club. I could get the 9 of spades. Or I could get the 9 of diamonds. So then what's going to be the probability that this will happen, that the event E will happen? Well, it looks like there are 4 things in that event, and there are 52 things in my sample space. So 4 out of 52, which reduces down to 1 out of 13. So then the probability is 1/13. Right? Now, one way to think about probability when it's reduced is to think about it from the idea of, if I were to run this experiment that many times, I'd see the result I want that many times. So if I went to a deck of cards and shuffled it and picked a card 13 times, pick a card, look, put it back, pick a card, look, put it back, pick a card, look, put it back 13 times, on average, I'd see a 9 one time out of every 13 picks. That does not mean that it absolutely will happen one time out of every 13 picks. It just means on average, if I run this experiment often enough. So if I sat down with a deck of cards and spent my entire Sunday doing nothing but looking at cards all day long, kept detailed records, at the end of the day, it would average out to be about 1 out of every 13. Okay. All right, a black card. Well, what is the probability that I will pick a black card? Well, here's what I know. It's going to be a fraction, and my denominator is going to be 52. So what is the event of black card? Well, if I go back up here and look, then that means I'm looking at the event either club or spade. And there are 13 spades. There are 13 clubs, so that means a grand total of 26 out of 52, which does reduce down to 1/2. If you're having trouble reducing fractions, remember your calculator can reduce fractions for you. So if I do 26 divided by 52, math, enter, enter, 1/2. Or if I use the fraction command and actually just type it in as that 26 over 52 and just press enter, it automatically reduces it for me. So if you're having trouble reducing fractions, or if you don't want to go through it, you can use your calculator to make that happen. All right, how about a black 9? All right, so now in terms of the language of probability, If we were to call that event F, then what we're looking at here is we're looking at E intersection F, because we're looking at the event E, which is a 9, intersected with the event F, which makes it both a black card and a 9, or a black 9. So then the probability of E intersection F is going to be something over 52. And now I got to figure out how many cards are in that intersection. Well, the intersection, what's going on there? The intersection of E and F is going to be the 9 of spades and the 9 of clubs. I'm not even going to try to draw them again. Okay? So the 9S and the 9C, 2 out of 52, 1 out of 26, probability. Right? How about the 9 of clubs? The 9 of clubs, that's just one card. So the probability of the 9 of clubs, 1 out of 52. How about the probability of a face card? Now you might have noticed that I'm not actually writing out every single event every single time. I kind of got them right here, don't I? I can just go back here and look at this and see them, right? All right, so face cards. Kings, queens, and jacks. There's 4 jacks, 4 queens, 4 kings, 4 times 3, 12. So I think the probability of a face card is going to be 12 out of 52. And then what does that reduce down to? Let's see. 52, 3/13. Right. And of course, if they want a decimal, I'll give them a decimal. If they want a fraction, I'll give them a fraction. If they want a percent, I'll give them a percent. Whatever the question asks for. Okay. All right. A black 7 or a red 8. Well, if I think of this as one event and this is another event, then if I thought that was A and that was B, then this would be the union of those two events. And A, the number of elements in A is going to be 4. The number of elements in B is going to be 4. And the number of elements in A union B, since those two sets are disjoint, is going to be 8. So then the probability of A union B would be 8 out of 52, which is 4 out of 26, which is 2 out of 13. Okay, let's change the experiment. An urn contains 3 red, 4 orange, 5 yellow, and 8 black marbles. If a marble is drawn at random, find the following probabilities. Now, I don't know why, but every time I see a problem in a probability book talking about marbles in something, they tend to be inside of an urn. I'm not even sure what an urn is here, but okay. I got a bunch of marbles in there, and I'm gonna reach in and pick one. My first probability is to find the probability that a red marble is picked. Well, my sample space is all of those marbles. So the number of elements in my sample space is going to be all of the marbles. So 3 and 4 and 5 and 8, well, 3 and 4 is 7 and 5 is 12 and 8 is 20. So there's 20 marbles in there. And how many of them are red? And so the probability of red is going to be the number of red divided by the number of elements in the sample space. 3/20. How about the probability of orange? Well, if you're looking at that saying that's the same problem again, then yeah, you're right. It's just switching out red for orange. 4/20, which does reduce down to, what is that going to go to, 1/5? And we should reduce when we can, right? All right. How about the probability the marble is not orange? Okay, so here's where we get into the idea of the complement, right? And the formula, the theory is this. The probability of the complement of an event is 1 minus the probability of the event. Okay? Think about it like this, right? If there's a 30% chance that it's going to rain today, That means that there's a 70% chance that it won't, because the total has to add up to 100%. And so that 100%, this 100%, that's the one that's right there. And so what we're saying here is that the probability of an event plus the probability of its complement must add up to 1. And then with a little bit of algebra, you can turn that into that. Okay? So the idea of the complement is the idea that we can find probabilities indirectly. Okay? The probability of an orange marble is easy to calculate. I just did it. It's 1/5. So the probability of not orange would then be the 4/5. And where'd 4/5 come from? 1 minus the 1/5, 4/5. Okay? All right, I've got an or down here. What's the probability of red or yellow? Red or yellow means red or yellow or both. Well, it can't be both red and yellow at the same time. It's just going to be the exclusive or here. There were 3 of those. There were 5 of those. So there are 8 favorable outcomes for this experiment. There are 20 elements in the sample space. So what's that? 4/10? 2/5? So my probability is 2/5. All right, so all the probabilities we've calculated so far have all been what's referred to as theoretical probability or classical probability, where we assume that the experiment is equally likely and we have a sample space well defined and all of that business. But there's another side to probability which is more commonly used, and that's the empirical probability side. The empirical probability side is where we don't have an experiment in the classic sense, like flipping a coin or rolling a die. We have data that's been gathered about a scenario, and then we use that data to calculate probabilities. So the idea of empirical probability is actually quite relevant, especially to business applications, because it's where the probability comes from when they calculate things like your, what's the word I'm looking for here? Insurance rates. Because they want to know what's the probability you're going to get in a car wreck. Well, probably you getting in a car wreck isn't about rolling a die or flipping a coin. It's what does the data show? For people your age, your gender, your socioeconomic status, your educational level, your whatever data they gather, what's the likelihood you'll get into a car wreck? And, there's a lot of that is applied. So this is where a lot of applicable probability lives, right? All right, so if you have a scenario where you do not have equally likely outcomes, we calculate probability, we use the similar formula, we use this formula right here. Probability of E is equal to F divided by N, where F here represents the frequency of the events in question, and that N here is the total of the data, we'll call it, collected. All right, so this is a classic example of empirical probability, and also leads us to something called Simpson's paradox, but we'll take a look at it. In 1973, the University of California, Berkeley's graduate school was concerned about a possible lawsuit for gender bias in their admissions. The following data were collected. So they collected a pile of data, and then they want to know some calculations here. Okay? All right, so let's take a look at some specific probabilities. So I'll start here with this one. What was the probability that a male applicant was admitted? So I want to find the probability that a male was admitted. Well, I'm going to make a fraction. My numerator is going to be the frequency of the event in question. That means that a male was admitted, and so that is going to be 1,198. And then my denominator is going to be the total number of the data collected, so that's going to be the males admitted plus the males rejected. Now, that's kind of useless, so I'm going to make it into something useful. I'm going to turn this into a percent. So that's going to be that 1198 divided by the quantity 1198 plus 1493. And it comes out to be about a 44.5%. So we'll just call that 44.5%. So based on the data that we've got here, according to the admissions, if you were a male, and you applied to graduate school, you had about a 44.5% chance of being admitted. What about the probability the female applicant was admitted? So what's the probability that a female was, admitted? Well, same logic. I'm going to use that fraction again. My numerator is going to be the number of admitted, so 557 divided by the total number that applied. The 557 that applied, the 1,278 that were denied. Grab my calculator. I'll do it the other way in case you want to see it. So that would be 557 over 557 plus 1,278. And I get that completely useless fraction. So I'll turn that into a decimal. And I get 30.4%. Okay. Now, right there on its face, it appears that there's a problem there. It appears that the men are getting admitted at a much higher rate than the women. The males that were admitted, they were admitted at a 44.5%. Females were admitted at 30.4%. That's like 14% difference. It's a lot. But when they looked a little bit deeper into the data and they broke it out by department, when they separated it by department, the results for the largest 6 departments were given as followed. Okay? And so now if we actually go and calculate these, so I'm bringing my calculator up, and we take a look at what happened. Let's look at Department A, and let's just do the males for now. So it was be 51 divided by 825. I get a 6.2%. for the males admitted. Okay? If I go to apartment B, 353 divided by 560, I get 63%. Okay? If I go to department C, 88 divided by 325, I'm finding probabilities by just making fractions here, 27.1%. If I go to department D, I got 138 divided by 417, 33.1. If I go to department E, what do we got here? We got 53 admitted divided by 191 applied. I get 27.7%. Remember, these are all percents. And then if I go to department F, I've got 22 admitted out of 373 that applied. I'm looking at, 5.9%. Okay. Let's do the same thing for the female applicants. 89 divided by 108. Whoops, can't see the equal sign. There you go. Change colors here. What was that again? That was 11 point, we'll call that 11.1. Next department, it's 17 out of 25. That's 68%. If I go to the next department, I got 281 divided by 593, 47.4%. If I go to the next department, it's 131, whoops, missing my one there, 131 divided by 375. I get 30, was that 34.5? Wait. 35%. Come on, eraser. I'll write it over here. For some reason, my tablet isn't responding. 94 divided by 393. 24%. 24 divided by 341. 7%. I want you to take a look at what happened here. Now, I'm just doing an example of empirical probability. That's what we're working on here. But I wanted to bring up something called Simpson's paradox. It also has other names because this guy isn't the first one to acknowledge it. But if you look, 6-2 to 11-1, more women, more females, more females, more females, more female. Oh, more men, more females. In 5 of the 6 largest departments on campus, where the most people applied, more males were admitted than females. But the rates flipped when we looked at it closely. Overall, more men were admitted than women. By department, more women than men for everything except for one. So this is something called Simpson's paradox. But the reason I bring it up isn't about Simpson's paradox. It's because I just want to make a brief statement about the misuse of statistics and the misuse of probability. That one of the issues that we have with probability and statistics in general is that the average person doesn't have enough fluency with them, enough experience with them to really be good at them. I mean, we can do probability calculations all day long, but what are we really saying when we say 44.5%? Or what are we really saying when we say 30.4%? We're trying to make a statement about the likelihood of something, right? But what is the thing that we're making a statement about? Because someone could look at this and make an argument that in 1973, University of California at Berkeley's graduate school had some sort of gender bias. When in fact they didn't. If anything, one could make an argument in the other direction, that the gender bias existed, but it was against the male applicants rather than the female applicants. And what it turned out to be is it wasn't a gender bias in either direction. It's just that there were, in general, more male applicants were applying to graduate schools where they were going to get admitted. It had a higher overall admission rate. And more female applicants were applying to the schools that had a lower application rate acceptance. And so it looked like it was one way, right? All right, so probability. What are we doing in this section? We're calculating basic probability. If I go back up here to the top, we started with the very, very generic, silly experiments, defining silly sample spaces. Who spins a spinner? Okay, outside of playing board games with the kids, we don't really spin spinners very often, but we can spin spinners and we can talk about the probability of something occurring. We can toss coins. We can flip the coins until things happen. We define sample spaces. We define events as a subset of a sample space. We set up probability by making fractions where the numerator is the number of elements in the event, denominator is the number of elements in the sample space. We only use this formula when we have those equally likely outcome experiments, right? When things switch to not equally likely, then we start talking about empirical or data-driven probability. We still use a fraction. The numerator is the frequency of the event in question, what we want to see. Our denominator is the total of the data collected. Be careful with the denominators. You may have noticed in my calculations, up here I had to add two numbers together to get my denominators. But down here, the denominators were given to me directly. I didn't have to add. So just be careful with your denominators that it actually is what you want it to be, and make those calculations. That brings us to the end of this. 7.4 is next. I'll see you next week for that one.